Yeah, the top one is open, and it's
Halloween.
cold air.
So that's why.
All right, welcome to Wonks. We have 3 talks, first of which is Aaron. He's going to be talking about APL, so take it away.
All right, thank you. Can everybody see that all right? I think I might risk blowing it up a little bigger. So I would like to say I'm going to be talking about APL, but for all you newbies, I apologize. You're not going to be getting an intro to APL at all. Instead, this is a short little, Roger would call it maybe an amuse-bouche of APL code that Roger Hui developed and demonstrated at Dyalog 17 this year. And it's a little algorithmic exploration of handling uniqueness algorithms. So it was fun. I liked it a lot. I thought it was kind of clever, and I thought it was a really neat expression of an algorithmic optimization technique expressed in a really concise way. So I like that. The problem is to compute x iota of x, which basically is the index lookup of x inside of itself, which means that we are, let's say x is a vector of strings. We're going to look into x and find the first occurrence of a given string inside of that x. And for every occurrence of that string, we'll return the index of that first occurrence. So, for example, let's initialize some random strings. So what we have here is basically all we did is we generated 10 random numbers, added 1 to them, took the reciprocal, and then converted them to strings. And so these are all a set of strings that are just textual representations of their indices, or of their values. So then the index selfie, as we call it, will give you the index where the first occurrence of that value appears. Good so far?
So you get a result that has as many entries as the original thing.
On the right, yeah, the right argument. As many entries as the right argument has. In this case, since it's a selfie, it doesn't matter. Right? So how do we implement this? This is the question. How do we implement this efficiently? There's the n squared solution, which every APLer would be able to whip out pretty quickly. And so what we're doing here is we get our x in, and we compare pairwise every value with every other value. And this gives us a matrix of Boolean values indicating which ones are equal to one another. Then we do a scan, an OR scan, along the columns. What that'll do is as soon as a 1 appears, everything else to the right of it will turn into a 1 as well. And so then if we sum up those columns, we get everything after, basically the count of everything after the first occurrence. So then we just subtract that from the total elements, and that'll give us our value. So we can give it a little bit more data. This is 1,000 elements. And I can verify that I get the same result. So ix of x gives us the same thing as our built-in. And now we can do a little benchmarking of the code. So what we're doing here is we're doing 5 values. So 1,000, 2,000, 4,000, so forth. And then we're going to time each one of those using some random data of that size. And we're going to store our timings inside of T and display the result. Now Compex will run XIX multiple times until it gets enough data to get an average timing result. Which is usually about a second, give or take, for each option. So we can see when it's small, pretty fast, but it grows somewhat quickly. The timing grows somewhat quickly, as we would expect, because this is a quadratic algorithm. So we can see the scaling, or how quickly it grows, by doing the n-wise division reduction over our timings. So what this means is we're going to take each of these pairs, so these two, etc., and we're going to divide the right one from the left one. And that'll show us basically the relative difference in timings between each of them, we can see that it's all about 4, which is about what we expect given how quick our size is. So let's improve this using hashing. So this one's a little funky, but basically this is our hash function. We're going to take in a string, look up the ASCII values for that character, think of them as ASCII values, and then treat that vector as a base 3 encoded number and convert that interpret it basically as a base 3 encoded number. And this is our new replacement for XIX. So what we're going to do is we're going to create a buffer to store all of our initial possible indexes that we're going to have. And then we're going to use this little key operation with our hash function, alpha alpha, which is going to be HF each. And what this will do is it'll find all of the things that are hashed according to the same hash and group them all together and give us the indices of those. And we're going to use those indices to look up the original values and then use our other quadratic algorithm on that cluster or grouped set of options, and then find the indices inside of that, use that to do a relative lookup into our original indices, and then store those into our buffer. Does that make sense? So what we're doing is we've got a hierarchical algorithm now, where we first partition into things based on their hashes. So we've clustered them. The idea being that hopefully those are smaller, and then we can use the quadratic algorithm on the small elements. So we can generate some new random numbers. And now we can compare them with a relatively small size, compare the original to this new one with HF map. You can think of this as the hash function mapped over every element with HIX. And you can see HIX is slower when we have very small number of elements, which is what we hope to have. And then we can compare how is this scaling. What are the timings as we scale up the number of elements we have? So 1,000 to 16,000. And we can compare our timings. And so you can already see this is looking a little bit better. But what's important here is our scaling factor is now much better. So rather than scaling quadratically like we had before, you see we're getting a very nice linear-ish type of scale. And so now we can generate a lot of data. Well, a lot of data for this small micro example. And we can do a comparison of what the performance difference is inside of there. And you can see that as soon as we get a few more values, this hashing algorithm allows us to greatly improve the performance by quite a significant margin. So the way that works is that we have, if we take our hashing function and we look, we get about 1,300 distinct partitions for those 16,000 elements. And the average size of any one of those is about 11, with 38 being our max and 1 being our min. So this is a nice little train saying what's the min, what's the max, and what's the average of the size of the partitions inside of our piece. And there you go. There's I think of it as a cute little algorithmic exploration where almost everything fits on this screen here. But that's our, and it's not actually that much more complicated than the original algorithm. A little bit more verbose, but fairly straightforward optimization and a clever little trick to leverage the key operator and using partitioning to optimize some of the performance. So I like these little tricks because they're really easy to imagine and implement, but they often can get you really, really good gains for certain problem sets. Yeah.
That hashing function, taking the base 3 interpretation of some bits, is that a common, like, low collision hash method?
It's not meant to be necessarily low collision. It's supposed to be something relatively useful for some data that we might get in. So it's not meant to be an ultra good cryptographically secure hashing function or something like this. It's meant to be, will this partition our data relatively evenly?
Would you use that in like other more general settings, or is it just happens to work well in this?
This is sort of a highly optimized hash function. Well, not highly optimized. It's a convenient hash function because it's very easy to implement. And it's very easy to implement low-level in C very fast. So, because this quad AB iota omega basically is a no-op. It costs nothing when you've got your strings represented as numbers in your interpreter, or wherever this is implemented. And then your base 3 encoding is very trivial as well, because you're basically just stripping off some bits and squashing them together. So it's just a bunch of bit masks.
So if we have more questions, let's do the swap first while we're asking questions. So any other questions for Aaron?
Oh, the HDMI works now.
Apparently.
Oh.
That's what I was using.
I used it last time.
Yeah.
Good to know.
All right, no other questions? All right, let's thank Aaron. You good? All right. So our next talk is by David. He's talking about felt. Take it away.
Hello, everybody. So many of you may have seen literate programming in the style of Knuth in the past. So this is an example of a terrible literate program, which sort of describes what's going on, and it has parts of the program pulled out. We've got sort of this star program macro saying what's the main program, and then we've lifted out little pieces and named them with brackets around them. I think most of Knuth's systems actually use 2 sets of brackets, but I got it wrong here, I'm sorry. And this is great if you want to write something like tech, where you have the implementation explaining itself in the form of a book, and you really want to get across sort of insights about algorithms and that sort of thing. But there are other kinds of literate programs where it doesn't necessarily make sense. But first off, how do we turn this into a program that we actually run? And how do we turn it into a document that we actually read? So the first step is to run our program. We use a process called tangling. So we start off with this literate program where some of the macros are kind of pushed away. And then the tangling process ditches the text and sticks in the macros. And then we've got our whole program, which we can then kick off to our favorite programming language and get it run. But then when we want to read a document, we use a process which is called weaving, which is meant to actually construct a document out of this. And I don't really have a good animation for that, so I just put it in computer modern. But because we've written the code with the intention that it be read as a document, less needs to be done. But sometimes all of this tangling and weaving isn't really what we want to do. We just want to write a program that looks like a program and have it be very convenient to describe the program as it is, rather than breaking it into little pieces and viewing the document as a kind of web structure which we explore in the process of reading and writing. And so in the Haskell world, they have what they call literate Haskell. And there's a million things out there that start with this blog post is literate Haskell. And then we put the little bird tracks over on the left, which say, this part is code, and everything without the greater than space is considered to be a giant comment. And this is I guess a somewhat satire of Haskell style. So we can say what language we're working in and all the extensions. And then we have some throwaway comment about importing libraries. Whereas in Knuth style literate programming, this stuff wouldn't be there in the document because it really doesn't matter all that much. We just arrange for it to disappear during the weaving process, whereas other things would go differently. And so Racket has a Knuth-style literate programming thing already, but I wanted to make some fancy lecture notes with embedded code. And if you're trying to teach someone how to write a certain kind of program, then it's not always the best to have it not look like a program. We want to write a program that looks like the programs they write, so we don't want to do any tangling and weaving. So I figured I'd be clever and call it felt, because that's cloth made without weaving. So So an example of what this is looking like in practice is I might write some little evaluator for lambda calculus. Wow, this is a low resolution projector. Okay. So I'm going to say I'm in #lang felt. And felt looks an awful lot like scribble/manual for those who know how it looks, except I've got this operator here called program. And what program does is it allows me to define, it's basically like the greater than signs in literate Haskell. It allows me to say, these regions of the document, when you interpret it as a program, get run. Ignore the rest. But then when we interpret it as an actual document to be read, we typeset them and hyperlink them. So if I come up and click my Scribble HTML button, it sits there and crunches for a little bit, and then I get out this web page. And note that it told me that I forgot to describe this structure appropriately with a little red angry underline. We can fix that. And then down here, my evaluator, I was able to write sort of Scribble-style documentation right next to the actual implementation. And if later on I see val, for example, in the implementation of apply, I can then click on it, and it'll jump me right to its description. So I get to sort of describe my program and write my program in one file without a lot of overhead, without needing to keep track of a whole new namespace of literate programming splice macros. And I get to use all of these Scribble features that I know of. And if the person who's the receiver of these lecture notes doesn't know what symbol means, they can click on it, and then they get to find out what it means as well. So we don't lose out on the nice sort of code navigation features that we have in our documentation system. Because the compiler knows what a name means. We should use that. Likewise, because this is Racket land, we need to be able to work with more than one language at a time. So felt can take an option, which is program lang. And here we can embed a type Racket program inside of felt. And it can import our other one. And then when I run Scribble HTML on it, sits there and thinks for a little bit. And we see that our val link is broken. That's no good. Luckily, however, we can include multiple modules in one big program, no matter what language the actual program itself is written in, and render that to HTML. We have to wait a little bit longer with the little garbage collection logo going on, but then we come here and scroll down to the type code, and we see that val now links to its documentation appropriately, because it was all kind of built together. At the end, I got 10 minutes right now. And if we want to get rid of any administrivia in the middle of the document as written, then we can suppress the bureaucratic details by using Scribble's comment syntax to actually make a legitimate comment. And then if we pass the hide option to the program, then it runs it only during the program phase. So you can see this as being kind of a compromise between traditional literate programming and sort of Haskell-style literate programming. And then, it works for real examples. Like I've got this nice big one right here, where if I pop in and show it, so I've got this big fancy tutorial with multiple modules and margin notes, and all this stuff is linked together. I can have a bibliography, pardon the Freudian slip there. And it seems to work out all right, I think. This is still like highly pre-alpha quality software, but it at least works for my one example. So ship it, I guess. That's all. Yeah. Question? I think you had your hand up in the middle, so you should go first.
What sense is close not described enough? Like, what does that scribble mean?
What it means is that that I haven't documented it. So if I want to make the scribble go away, yeah, I'll make the scribble go away. So I can come up here and say def struct star, and then it's close, and it's got.
You have to have use scribble to document.
Yeah, exactly, and that makes it into a link target.
I see. Okay. Otherwise,
because the links are to the description of it, not to the implementation of it. I can put them next to each other, great. And for things like structs, sometimes you even want to just suppress the implementation in the output. Yeah.
So you said this is without weaving, but it seems like this is without tangling.
Sorry. Yeah, I was being overly clever.
Okay, so
Yeah.
you're not tangling, but you are still weaving.
It's true.
Okay.
Yeah. Maybe I should call it braiding. Yeah.
So one thing that Literate has to, I hope, lets me do like it is if I'm writing a function that's defining several clauses, I can put text between those clauses.
Right.
And I can explain each clause separately. How might I do it here? Because there are no clauses in most Racket languages.
Right. So the first step is to define a language which has these clauses and then use it.
I don't get to have text inside of programs, like kind of recursively.
Yeah, you can include you can do that. There is
Okay,
there is
that's what
there
I
is an
was-
escape from so
Like
that's
there I see a match, right? So I'll explain each match clause separately.
yeah. So you can do it in comment form and then
This is still like Scribble in that it doesn't have proper chunking.
what do you mean by chunking?
So you would, in order to abstract code fragments in the way that a traditional web program would, you would have to use the macro system.
For doing that, you would use Scribble LP, which is the thing I didn't want to use.
Right.
That already exists. Yeah.
And so you're intentionally simplifying this by only having one program construct.
Yes.
And then, so it would be in the class of the semi-literate program.
Yes. Yeah. So because for showing how to write a particular kind of program, as you would without it, I think that's the right approach. Whereas if it's traditional literate programming, this is not what you want. I think I'm out of time. So if you want to talk about this, grab me after.
Racket yet?
Very soon. As soon as I figure out how to get its docs to work right, then it'll happen.
All right, next speaker is Rajan. He's talking about building high-performance DSLs in Racket. Take it away.
What does it mean? Like, there are like 6-7 words on there. Like, what does it mean? I guess everyone knows what Racket means, and like, in Racket and building. But what's high performance DSL? Like, what do you mean by high performance?
Goes fast.
Goes fast. That's the first thing that comes to mind.
Uses less RAM.
Polynomial sign.
Classifies newsgroups articles accurately.
And in time, in 2 seconds. Yeah, so high performance for me means it runs fast, right? And DSLs kind of means, it means domain specific language, but it's sort of like not full language, like small language that you know that you're trying to like experiment with, and maybe at some point you want to improve it in terms of performance. So how does that happen? So when you go to the front page of Racket, or like just open the Racket lang or go to the Wikipedia, you see this everywhere. Racket is a language for creating languages, right? And I took this like, it's in quotes. I took it directly from the website. And this is also like mentioned every time someone is like trying to entice other people to use Racket. It's like, hey, you see this hash lang, and you can make your own like felt or other pi or other stuff. So you can do all sorts of stuff, and that's what like differentiates Racket. Like one of the biggest differentiation of Racket when it comes to comparing it to other languages, because you can do like, it already gives you like Racket base, it gives you type Racket, and there are like lazy Racket as well. And there are a bunch of student languages for teaching students and like reducing the complete language to a smaller form, so it's easier for them to learn. And you can do all sorts of things like this. But how does it work inside? So usually you can do like maybe something like this. So you have a hash lang A that you implemented, and you have a hash lang B. If you really did it carefully and you wanted it, you can like intercommunicate between each other. You can like use call functions from hash lang B in A and functions from A in B and all those stuff. And that happens because everything is on Racket VM. At the end, any language you implement in Racket, it goes and expands into Racket bytecode and runs on VM. You can do other things like Scribble, but most of the languages are done like that. So I want to do it a different way, right? Let's say hash lang C. Now it's like A, B, C. Also think of C. Right? I want to do hash lang C, which runs as fast as C. I want it to be run as fast as C, maybe faster. I don't know. and I want to use a different compiler. I don't want to use Racket VM. It's slow. I guess that's why they are like switching it to Shade. But anyways, like for me, it's slow. It doesn't run that fast, especially if you have a DSL. DSLs are usually very small languages, and when somebody is implementing a DSL, they know a lot about those languages, and there can be a lot of like optimization that can come out of from the semantics of that language, and you wanna use all of that, and you want to use a different compiler, and you want this. These arrows are what's difficult. I mean, I guess you can right now do this stuff still, like hash lang C, expand it to like C, write it to file, compile it, and figure out a way to do like arrows. It's kind of really hard. Like you have to jump through a lot of hoops to do that. So how do we solve this problem? As we all are programming language people, we make a language for it, right? I mean, Racket allows us making language. So what? We make hash lang compiler or something. I mean, I haven't done this. This is like this is like pie in the sky. This is like what I want. This is like what I want to be there. Why is it not there? When you say Racket is a programming language for creating languages, where's the compiler? I thought compiler is like the biggest part of language. So I want something like this, and I want this with this picture. I want all this to happen, and I also want to like do it pretty easily. Think of like you can think of this language. You can think a lot of things about how this language might look like. If anyone has used Redx, think of Redx, but as a compiler. You say, this is my grammar, this is my language, these are my semantics. Give me a good performant compiler, not the Redx one. I mean, Redx gives you an interpreter, but like takes years to. Right? So how do we go there? And I'm sort of like using a bottom-up approach. We start from the bottom, and that's like our goal. That's where we want, right? So what's the bottom? Bottom is a sham. It's literally a sham. You can go to the website and see. And what is it? So when you look at the picture that I showed you, there were like a bunch of arrows there. But what I have right now is this. There's only one arrow going one way. And there's the little sham, and there's a small box inside the sham which is called LLVM. I hope everyone knows what it is. So what does it gives us? Now, what does it give us? Does it give me all the things that I want? Maybe somehow. So what does sham gives you? What can it do for you? It can compile code. Yay. It can do it at runtime. You are running your program, and at some point while running it, you want to compile some function in a specific way. You can like do specializations and all those things. So yay! And you saw one arrow, right? So it's sort of like when you compile it, it can wrap it up and give it to Racket. And you can use your Racket programs to use the compiled code that you compiled specifically by yourself using LLVM, but not directly LLVM, because you're using the sham, which gives you some abstractions, kind of makes it easier. And it also gives you a couple other compiler-related stuff, like optimizations, like vectorization, loop hosting, all this stuff. What do I want in future? This is like what I want. I want a simpler abstraction over sham. Right now, if you go look at sham, this slide, I had no code. I didn't want to show any code because I want you to imagine what you want when you think about this. So I want a simpler abstraction over sham, and I want to figure out how we can define #lang compiler. Like, what does it even mean by a language for making compilers? What does it have? Does it have libraries which do specific optimizations? Can you pull those libraries into your own compiler without doing much stuff? And like use someone else's like small part of compiler, like import C just the function once, or just the structs and give it to me, or like use it. Right now we only have LLVM, like use Haskell core, use Beam, whatever I want to use, you should be able to use it. I mean, Racket is a language for defining languages, and I want to use all the languages in the world from Racket. That's what I want. And sort of, I also want the other arrow to be there. Like, going from Racket into something else is easy, other ways hard. And the last part is the most important one, which sham doesn't give you. Don't give segfaults to your users. That's what it is. I guess my time is up. Any questions?
I have an extra bullet for the future. I want the expander to be sped up for any given language.
I think that they are trying to do that somehow.
We're
getting shape.
Yeah,
that's not fast enough.
And I don't know if they're going the right way, because they're writing the expander in Racket now, which was before recurrency. So I think they're going into the opposite way. But like write a compiler for expander.
If you have compiler,
right?
then you can write your expander in this super language that's super fast.
Yeah. So use #lang compiler to make #lang expander, right? We are PL people. How do we solve problems? We solve problems by making languages, right? #lang APL. I want #lang APL, right? Without all those weird symbols.
I could show you how to make Dr. Racket take keyboard input into the APL keyboard layout.
I don't.
Yes, you do, man. Yes, you do.
I want APL with S expressions. Any other questions?
I want a sweet lemon too.
Any other questions? I mean, all of this was a pie in the sky, but using sham, we've been able. I have written a JIT for Haku, and it's up there and stunning. And like, if you want to compare numbers, it's sort of like earlier implemented in Haskell, and now it's like 30 times, 40 times faster when we do it. Because it's like a very small core language, which has just arrays. It doesn't concatenate arrays. So you can do like all sorts of array optimization techniques that you know, and you can do it directly on Metal. And then you can use that from Racket. You don't have to know anything about that. It'll just compile it for you, give it to you as a Racket function.
Wasn't JIT in the Racket supposed to solve all these problems?
I don't know.
Right.
I wasn't there at
JIT that isn't aware that it's running Racket. It's just a default, it's a generic JIT.
Alright. I just remember like
It's not
10 years ago, like, oh, Racket's got a JIT now. Performance problems are over.
Yeah, but you can go and use the internals of that JIT to make your own JIT. I want to be able to write my own JIT. Maybe I want a tracing JIT, and I want to be able to write that in Racket. I mean, if you sort of like building, Racket is a language for building programming language. So compiler is a big part of programming language, and I want to be able to do all that stuff in Racket. And that's the goal. And like, if you have other bullet points, I'm happy. I want more bullet points, because right now I don't know what hashline compilers look like.
ML.
Oh, sorry. Any other questions?
Now let's thank all three of our speakers.